Electric fields and potential. Describe how to measure the strength of an electric field at different points. Describe how electric fields are represented by vectors and by electric field lines. Describe how objects can be completely shielded by electric fields. Explain why a charged object in an electric field is considered to have electric potential energy. Distinguish between electric potential energy and electric potential. Describe how electrical energy can be stored. Describe the operation of a Van de Graaff generator. The big idea: an electric field is a storehouse of energy. The space around a strong magnetic is different from how it would be if the magnet were not there. Put a paperclip in the space and you'll see the paperclip move. The space around the sun is different from how it would be if the sun were not there. The sun's gravitational influence affects the motions of the planets around it. Similarly, the space around a concentration of electric charge is difficult from how it would be if the charge were not there. If you walk by the charged dome of an electrostatic machine, a Van de Graaff generator, for example, you can sense the charge. Hair on your body stands out just a tiny bit if you're more than a meter away, and more if you're closer. The space that surrounds each of these things, the magnet, the sun, and the electric charge, is altered. The space is said to contain a force field. What is electric shielding? Wrap a cellular phone completely with aluminum foil. Make a call to the wrapped phone. Unwrap the cell phone and now cover only part of it with foil. Make a call to the partly wrapped cell phone. Repeat step 3 a few more times, covering different parts of the phone. Analyze and conclude, observing what effect did completely wrapping the phone have on reception. Did wrapping only part of the phone block the incoming signal? If so, which part of the phone needed to be covered in order to block the signal? Predicting. What other materials do you think could be used to shield a cell phone? Making generalizations. What is electric shielding and why does it work? 33.1 Electric fields. The force field that surrounds a mass is a gravitational field. If you throw a ball into the air, it follows a curved path. Earlier chapters showed that it curves because there is an interaction between the ball and Earth, between their centers of gravity to be exact. Their centers of gravity are quite far apart, so this is action at a distance. The idea that things not in contact could exert forces on one another bothered Isaac Newton and many others. The concept of a force field explains how Earth can exert a force on things without touching them, like a tossed ball. The ball is in contact with the Earth all the time. The ball curves because it interacts with Earth's gravitational field. 33.1. You can sense the force field that surrounds a charged Van de Graaff generator. You can think of distant space probes as interacting with gravitational fields rather than with masses of Earth and other astronomical bodies that are responsible for the fields. Just as the space around Earth and every other mass is filled with gravitational field, the space around every electric charge is filled with an electric field. An electric field is a force field that surrounds an electric charge or group of charges. In figure 33.2, a gravitational force holds a satellite in orbit about the planet, and an electric force holds an electron in orbit around a proton. In both cases, there is no contact between the objects, and the forces are acting at a distance. In terms of the field concept, the satellite and electron interact with the force fields of the planet and the proton and are everywhere in contact with these fields. Figure 33.2, the satellite and electron both experience forces. They are both in force fields. Just as in the gravitational case, the force that one electrical charge exerts on another can be described as the interaction between one charge and the electric field set up by the other. An electric field has both magnitude and direction. The magnitude, strength of the electric field can be measured by its effect on charges located in the field. Imagine a small positive test charge that is placed in an electric field. Where the force is greatest on the test charge, the field is the strongest. Where the force on the test charge is weak, the field is small. The direction of an electric field at any point by convention is the direction of the electrical force on a small positive test charge placed at any point. Thus, if the charge that sets up a field is positive, the field points away from that charge. If the charge that sets up the field is negative, the field points towards the charge. Be sure to distinguish between the hypothetical small test charge and the charge that sets up the field. Notes: the force on a charged particle gives the electric field strength E. In the equation, E equals F over Q. Concept check. How are the magnitude and direction of an electric field determined? 33.2 Electric field lines. Since an electric field has both magnitude and direction, it is a vector quantity and can be represented by vectors. The negatively charged particle in figure 33.3a is surrounded by vectors that points toward the particle. If the particle were positively charged, the vectors would point away from the particle. The vectors always point in the direction of the force that would act on a positive test charge. The magnitude of the field is indicated by the length of the vectors. The electric field is shorter where the vectors are long than it is where the vectors are short. Figure 33.3a, in a vector representation of an electric field, the length of the vectors indicates the magnitude of the field. B, in a line of force representation, the distance between field lines indicates magnitudes. To represent a complete electric field by vectors, you would have to show a vector in every direction in the space around the charge. Such a diagram would be totally unreadable. A more useful way to describe an electric field is shown in 33.3b. You can use electric field lines, also called lines of force, to represent an electric field. Where the lines are farther apart, the field is weaker. For an isolated charge, the lines extend to infinity, while for two or more opposite charges, the lines emanate from a positive charge and terminate on the negative charge. Some electric field configurations are shown in figure 33.4. Figure 33.4a. The field lines around a single positive charge extend to infinity. B, for a pair of equal but opposite charges, the field lines emanate from the positive charge and terminate on the negative charge. C, field lines are evenly spaced between two oppositely charged capacitor plates. Think. A beam of electrons is produced at one end of a glass tube and lights up a phosphor screen at the other end. When the beam is straight, it produces a spot in the middle of the screen. If the beam passes through an electric field of a pair of oppositely charged plates, it is deflected upward as shown. If the charges on the plates are reversed, In what direction will the beam deflect? When the charge on the plates is reversed, the electric field will be in the opposite direction, so the electron beam will be deflected upward. If the field is made to oscillate, the beam will be swept up and down. With a second set of plates and further refinements, it could sweep a picture onto a screen. Think television. The photographs in figure 33.5 show bits of thread that are suspended in an oil bath surrounding charged conductors. The ends of the bits of thread line up end to end with the electric field lines. In figure 33.5a and 33.5b, we see the field lines are characteristic of a single pair of point charges. The oppositely charged parallel plates in figure 33.5c produce nearly parallel field lines between the plates. Except near the ends, the field between the plates has a constant strength. Notice that in figure 33.5d, there is no electric field inside the charged cylinder. The conductor shields the space from the field outside. Concept check. How can you represent an electric field? 33.5. Bits of fine thread suspended in an oil bath surrounding charged conductors line up end to end along the direction of the field. The photos illustrate field patterns for A. Equal and opposite charges, B. Equal like charges, C. Oppositely charged plates, and D. Oppositely charged cylinder and plate. 33.3. Electric shielding. The dramatic photo in figure 33.6 shows a car being struck by lightning, yet the occupant inside the car is completely safe. This is because the electrons that shower down upon the car are mutually repelled and spread over the outer metal surface, finally discharging when additional sparks jump from the car's body to the ground. The configuration of electrons on the car's surface at any moment is such that the electric field inside the car practically cancel to zero. This is true of any charged conductor. If the charge on a conductor is not moving, the electric field inside the conductor is exactly zero. Figure 33.6. Electrons from a lightning bolt mutually repel and spread over the outer metal surface. The overall electric field inside the car practically cancels to zero. Charged conductors. The absence of electric field within a conductor holding static charge does not arise from the inability of an electric field to penetrate metals. It comes about because free electrons within the conductor can settle down and stop moving only when the electric field is zero. So the charges arrange themselves to ensure a zero field with the material. Consider the charged metal sphere in figure 33.7. Because of mutual repulsion, the electrons spread as far apart from one another as possible. They distribute themselves uniformly over the surface of the sphere. A positive test charge located exactly in the middle of the sphere would feel no force. Figure 33.7, charge located inside a charged hollow sphere cancel to zero. Figure 33.8. Static charges are distributed on the surface of all conductors in such a way that the electric field inside the conductors is zero. The electrons on the left side of a sphere would tend to pull the test charge to the left, but electrons on the right side of the sphere would tend to pull the test charge to the right equally hard. the net force on the test charge would be zero. Thus, the electric field is always zero. Interestingly enough, complete cancellation will occur anywhere inside the sphere. If the conductor is not spherical, then the charge distribution will not be uniform. The remarkable thing is this: the exact charge distribution over the surface is such that the electric field everywhere inside the conductor is zero. Look at it this way. If there were an electric field inside a conductor, then free electrons inside the conductor would be set in motion. How far would they move? Until equilibrium is established, which is to say, when the positions of all electrons produce a zero field inside the conductor. How to shield an electric field? There is no way to shield gravity because gravity only attracts. There are no repelling parts of gravity to offset attracting parts. Shielding electric fields, however, is quite simple. Surround yourself or whatever you wish to shield with a conducting surface. Put this surface in an electric field of whatever field strength. The free charges in the conducting surface will arrange themselves on the surface of the conductor in such a way that all field contributions inside cancel one another. Figure 33.9. The metal line cover shields the internal electric components from external electric fields. Similarly, a metal cover shields the coaxial cable. That's why certain electronic components are encased in metal boxes and why certain cables have a metal covering to shield them from all outside electrical activity. Concept check. How can you describe an electric field within a conductor holding static charge? Think. It is said that a gravitational field, unlike an electric field, cannot be shielded. But the gravitational field at the center of the Earth cancels to zero. Isn't this evidence that a gravitational field can be shielded? Think. No. Gravity can be canceled inside a planet or between planets, but it cannot be shielded by a planet or by any arrangement of masses. During a lunar eclipse, for example, when Earth is directly between the sun and the moon, there is no shielding of the sun's field to affect the moon's orbit. Even a very slight shielding would accumulate over a period of years and show itself in the timing of subsequent eclipses. Shielding requires a combination of repelling and attracting forces, and gravity only attracts. 33.4. Electrical potential energy. Recall the relationship between work and potential energy. Work is done when a force moves something in the direction of the force. An object has potential energy by virtue of its location, say in a force field. For example, if you lift an object, you apply a force equal to its weight. When you raise it through some distance, you are doing work on the object. You are also increasing its gravitational potential energy. The greater the distance it is raised, the greater is the increase in its gravitational potential energy. Doing work increases its gravitational potential energy as shown in figure 3310A. In a similar way, a charged object can have potential energy by virtue of its location in an electric field. 3310. A. Work is done to lift the mass against the gravitational field of Earth. In an elevated position, the mass has gravitational potential energy. When released, this energy is transferred to the piling below. B. Similar energy transfer occurs for electric charges. Just as work is required to lift an object against the gravitational field of Earth, work is required to push a charged particle against the electric field of a charged body. It may be more difficult to visualize, but the physics of both the gravitational case and the electrical case is the same. The electrical potential energy of a charged particle is increased when work is done to push it against the electric field of something else that is charged. Figure 3311A shows a small positive charge located at some distance from the positively charged sphere. Figure 3311. The small positive charge has more potential energy when it is closer to the positively charged sphere because work is required to move it to the closer location. If we push the small charge closer to the sphere, figure 3311b, we will expand energy to overcome electrical repulsion. Just as work is done in compressing a spring, work is done in pushing the charge against the electric field of the sphere. This work is equal to the energy gained by the charge. The energy a charge has due to its location in an electric field is called electrical potential energy. If the charge is released, it will accelerate in a direction away from the sphere, and its electrical potential energy will transform into kinetic energy. Concept checked. How can you increase the electrical potential energy of a charged particle? Figure 3311. The small positive charge has more potential energy when it is closer to the positively charged sphere because work is required to move it to the closer location. 33.5. Electric potential. If in the preceding discussion we push two charges instead, we do twice as much work. The two charges in the same location will have twice the electric potential energy as one. A group of 10 charges will have 10 times the potential energy, and so on. Rather than deal with the total potential energy of a group of charges, it is convenient when working with electricity to consider the electrical potential energy per charge. The electrical potential energy per charge is the total electric potential energy divided by the amount of charge. At any location, the potential energy per charge, whatever the amount of charge, will be the same. For example, an object with 10 units of charge at a specific location has 10 times as much potential energy as an object with a single unit of charge, but it also has 10 times as much charge, so the potential energy per charge is the same. The concept of electrical potential energy per charge has a special name: electric potential. Electric potential equals electrical potential energy per charge. Electrical potential is not the same as electrical potential energy. Electric potential is electrical potential per charge. Figure 3312. An object of greater charge has more potential energy in the field of a charged dome than an object of less charge, but the electric potential of any amount of charge at the same location is the same. The SI unit of measurement for electric potential is the volt, named after the Italian physicist Alessandro Volta, 1745 to 1827. The symbol for volt is V. Since potential energy is measured in joules and charge is measured in coulombs, 1 volt equals 1 joule per coulomb. Thus, a potential of 1 volt equals 1 joule of energy per coulomb of charge. 1,000 volts equals 1,000 joules of energy per coulomb of charge. If a conductor has a potential of 1,000 volts, it would take 1,000 joules of energy per coulomb to bring a small charge from very far away and add it to the charge on the conductor. 3313. Although the voltage of the charged balloon is high, the electrical potential energy is low because of the small amount of charge. Since the small charge would be much less than 1 coulomb, the energy required would be much less than 1,000 joules. For example, to add the charge of 1 proton to the conductor, 1 times 10 to the negative 16th coulombs, it would take only 1.6 times 10 to the negative 16 joules of energy. Since electrical potential is measured in volts, it is commonly called voltage. In this book, the names will be used interchangeably. The significance of voltage is that once the location of zero voltage has been specified, a definite value for it can be assigned to a location whether or not a charge exists at that location. We can speak about voltages at different locations in an electric field whether or not any changes occupy those locations. Rub a balloon on your hair and the balloon becomes negatively charged, perhaps to several thousand volts. If the charge on the balloon were 1 coulomb, it would take several thousand joules of energy to give the balloon that voltage. Notes: distinguish between electric potential energy and electric potential is high-level physics. Think, if there were twice as much charge on one of the charged objects near the charged sphere in figure 3312, would the electrical potential energy of the object in the field of the charged sphere be the same, or would it be twice as great? Would the electrical potential of the object be the same, or would it be twice as great? Twice as much charge would cause the object to have twice as much electrical potential energy because it would have taken twice as much work to bring the object to that location. But the electric potential would be the same because the electric potential is total electric potential energy divided by total charge. In this case, twice the energy divided by twice the charge gives the same value as the original energy divided by the original charge. However, 1 coulomb is a very large amount of charge. The charge on a balloon rubbed on hair is typically much less than a millionth of a coulomb. Therefore, the amount of energy associated with the charged balloon is very, very small, about 1,000th of a joule. A high voltage requires great energy only if a great amount of charge is involved. This example highlights the difference between electrical potential energy and electric potential. Concept check. What is the difference between electric potential and electrical potential energy? 33.6. Electrical energy storage. Electrical energy can be stored in a common device called a capacitor. Capacitors are found in nearly all electronic circuits. Computer memories use very tiny capacitors to store the ones and zeros of the binary code. Some keyboards have them beneath each key. Capacitors in photo flash units store larger amounts of energy slowly and release it rapidly during the short duration of the flash. Similarly, but on a grander scale, enormous amounts of energy are stored in banks of capacitors that power giant lasers in national laboratories. The simplest capacitor is a pair of conducting plates separated by a small distance, but not touching each other. When the plates are connected to a charging device, such as a battery shown in figure 3314, charge is transferred from one plate to the other. This occurs as the positive battery terminal pulls electrons from the plate connecting to it. These electrons, in effect, are pumped through the battery and through the negative terminal to the opposite plate. The capacitor plates then have equal and opposite charges. The positive plate is connected to the positive battery terminal, and the negative plate is connected to the negative battery terminal. The charging process is complete when the potential difference between the plates equals the potential difference between the battery terminals, the battery voltage. Figure 3314, a simple capacitor consists of two closely spaced metal parallel plates. When connected to a battery, the plates become equally and oppositely charged. The greater the battery voltage and the larger and closer the plates, the greater the charge that is stored. In practice, the plates may be thin metallic foils separated by a thin sheet of paper. This paper sandwich is then rolled up to save space and may be inserted into a cylinder. Such a practical capacitor is shown with others in figure 3315. We will consider the role of capacitors in circuits in the next chapter. Capacitors store and hold electric charges until discharged. A charged capacitor is discharged when a conducting path is provided between the plates. Note that a capacitor might store charge even after the electricity to a device has been turned off for seconds, minutes, or even longer. Figure 3315. In these capacitors, the plates consist of thin metallic foil that have been rolled up into a cylinder. Discharging a capacitor can be a shocking experience if you happen to be the conducting path. The energy transfer can be fatal where high voltages are present. That's the main reason for the warning labels on devices such as TV sets. The energy stored in a capacitor comes from the work done to charge it. The energy is in the form of the electric field between its plates. Between parallel plates, the electric field is uniform, as indicated in figure 33.4c and 33.5c on previous pages. So the energy stored in a capacitor is energy stored in the electric field. The electric fields are storehouses of energy. Figure 3316, capacitor plates with a dielectric. We will see in the next chapter that energy can be transported over long distances by electric fields, which can be directed through and guided by metal wires or directed through empty space. In chapter 37, we will see how energy from the sun is radiated in the form of electric and magnetic fields. The fact that energy is contained in electric fields is truly far-reaching. Concept check. Where does energy stored in a capacitor come from? Inkjet printers linked to technology. The printhead of an inkjet printer typically ejects a thin, steady stream of thousands of tiny ink droplets each second as it shuttles back and forth across the paper. As the stream flows between electrodes that are controlled by the computer, selective droplets are charged. The uncharged droplets then pass undeflected in the electric field of the parallel plate capacitor and form the image on the paper. The charged droplets are deflected and do not reach the page. Thus, the image produced on the paper is made from ink droplets that are not charged. The blank spaces correspond to deflected ink that never made it to the paper. Here is a schematic to peruse relative to inkjet printers. And another schematic for an inkjet printer. (33.7) The Van de Graaff generator. A common laboratory device for building up high voltage is the Van de Graaff generator. This is the lightning machine often used by evil scientists in old science fiction movies. A simple model of a Van de Graaff generator is shown in figure 3317. A large, hollow metal sphere is supported by a cylindrical insulating stand. A motor-driven rubber belt inside the support stand moves past a comb-like set of metal needles that are maintained at a high electric potential. The description here does seem incredibly evil. A continuous supply of electrons is deposited on the belt through electric discharge by the points of the needle and is carried up into the hollow metal sphere. Figure 3317. In a Van de Graaff generator, a moving rubber belt carries electrons from the voltage source to a conducting sphere. I'll let this run a few seconds so you can study the diagram. The electrons leak onto metal points which act like tiny lightning rods attached to the inner surface of the sphere. Because of mutual repulsion, the electrons move to the outer surface of the conducting sphere. Remember, static charge on a conductor is on the outer surface. This leaves the inside surface uncharged and able to receive more electrons as they are brought up from the belt. The process is continuous and the charge builds up to a very high electric potential on the order of millions of volts. Touching a Van de Graaff generator can be a hair-raising experience as shown in figure 3318. Figure 3318, demo of a Van de Graaff generator, are charged to a high voltage. A sphere with a radius of 1 meter can be raised to a potential of 3 million volts before electric discharge occurs through the air, because breakdown occurs in air when the electric field strength is about 3 million volts per meter. The voltage of a Van de Graaff generator can be increased by increasing the radius of the sphere or by placing the entire system in a container filled with high-pressure gas. Van de Graaff generators in pressurized gas can produce voltages as high as 20 million volts. These devices accelerate charged particles used as projectiles for penetrating the nuclei of atoms. Notes: an electric field is nature's storehouse of chemical energy. Concept check. How can the voltage of a Van de Graaff generator be increased? Summary: electric fields and potential. The magnitude, the strength of an electric field can be measured by its effect on charges located in the field. The direction of the electric field at any point is the direction of the electrical force on a small positive test charge. You can use electric field lines, also called lines of force, to represent an electric field. Where the lines are farther apart, the field is weaker. If the charge on a conductor is not moving, the electric field inside the conductor is exactly zero. The electric potential energy of a charged particle is increased when work is done to push it against the electric field of something else that is charged. Electric potential is not the same as electric potential energy. Electric potential is electric potential energy per charge. The energy stored in a capacitor comes from the work done to charge it. The voltage of a Van de Graaff generator can be increased by increasing the radius of the sphere or by placing the system in a container filled with high pressure gas.